So I just wanted to walk you through a couple of these sampling distribution problems. The way you have any questions, hopefully this video tutorial can help you get the answers to those questions. All right. So we're gonna look at some of these problems. We're gonna talk mainly about the central limit theorem and proportions and means, right? When we have sample sizes. So let's look at this first one, especially in that do now. It says the distance that Jonathan can throw a shot put is skewed to the right with a mean of 14.2 meters and a standard deviation of 3.5 meters. Over the course of a month, Jonathan makes 75 throws during practice. Assume these throws can be considered a random sample of Jonathan's shot put throws. What is the probability that Jonathan's average shot put distance for the month will be over 15 meters? So remember when we do stuff like this, a couple things we're looking for. We are looking for things that talk about means and standard deviations. When we talk about means and standard deviations, we want to try to make them normal. In order for it to be normal from this, it either needs to say that it's normal or we're looking for a sample size. In this case, we have a sample size where it tells us that he makes 75 throws. So my n is equal to 75. That is significant because we know that that number is bigger than 30. And if n is greater than or equal to 30, then by CLT, we can use the central limit theorem, and it tells us that the distribution of x bar is approximately normal with a mean of the population. In this case, his mean was 14.2 for the population value, and a standard deviation that is equal to, or we call it the standard error now, the standard deviation for the population, which is 3.5 meters. And because we have a sample size now, we need to make sure we divide that by the square root of our n value, which is 75 here. When we do that, we get a standard error that is equal to, we'll round to 3 decimals, 0.404. And so now, because the distribution is normal, and I have a mean for this particular distribution, I can draw a normal curve. And on this normal curve, remember the mean goes in the middle. So place our mean at 14.2, right? And they want to know what is the probability that he has throws that are over 15 meters. 15 meters is going to sit to the right of that 14.2. So we'll be over here at 15, and over that means we need to shade this to the right. Well, this is just a normal probability, so we'll use normal CDF in our calculators, right? And normal CDF, we know that the mean of we know that the lower bound, looking at this curve, the lower bound starts at 15, and it goes up to, remember, a bunch of nines. The mean of the distribution is just 14.2, and our new standard deviation, or what we call our standard error, is going to be equal to 0.404. So we plug that into a calculator, and we'll get a value that's equal to probability that your x bar here is greater than 15 is equal to 0.0239. So it looks like the answer here is going to be B. Now, these next two problems, if you look at number one, it talks about what is basically a statistic or a parameter. And remember that the parameter in the distribution is what we call our true value. And it comes from the population. It's the population value. And the statistic is what we call an estimate. And the estimates always come from the sample. So it says that a survey conducted by Black Flag asks whether or not the action of a certain type of roach disc was effective in killing roaches. 79% of the respondents agreed that the roach disc was effective. The number 79 is, and look, this 79% of the respondents, so they made up the sample in the survey. The sample, and because it comes from the sample, that 79% represents a statistic here. This is a statistic. All right. So that is another thing we need to worry about. Is going to be whether it's a parameter or a statistic. And then this next question talks about sampling variability. So we take many simple random samples from the same population, we'd expect basically. So remember that when we take, every population has some true value that we want to find, and value is called the parameter. But when we take samples, my sample may be different from your sample, and that's because we have what's called sampling variability. And if you think about, let's think about average height, for instance. If people are all around the average height, when we take many samples and look at the averages, we expect the averages to fall right around or about the same numbers. However, we'll have some averages that are very small, some averages are very large. But those numbers will be very small. Those amounts will be very small. So if you think about it, it's how we get our bell shape. Because we have everybody centering around some certain value, and as you move further out, those values get smaller and smaller and smaller. So this says if we take many simple random samples from the same population, would we expect the same values of the statistic for each sample? The values of the statistic will vary from sample to sample. A different value of the parameter for each sample, a problem with the voluntary response, or a problem with bias. So in this case, here's what we don't expect. We do not expect a different value of the parameter for each sample because the parameter is a true value. It is a set value already. We also don't expect the same values of the statistic for each sample because the statistic is based on the sample that you take. D and E are not going to actually talk about this problem. So my only answer here left is going to be B. And that's because the values will vary from sample to sample. We talked about that. That's called sampling variability. In this last problem, it says, what is the range of a sample size the research could take from this population without violating conditions required for this application here? In order to actually use this right here, this is called our standard error. This is called the standard error. And if we know nothing about the population, then remember, in order to use this value, the range, they're talking about the range, n has to be greater than or equal to 30. This is our central limit theorem. That's CLT. So the central limit theorem or standard error applies when you're actually talking about the central limit theorem. So this next example is going to talk about the central limit theorem, how we apply it to distributions that aren't normally distributed. So it says the histogram below was obtained from the data on 750 high school basketball games in the regional athletic conference. It represents the number of three-point baskets made in each game. So it's using that, a researcher takes a simple random sample of size 40 from this population and calculates the mean number of three-point baskets, which is the following best describes the shape. Remember when we talk about describing the shape, we're talking about what is the mean of standard deviation, or the shape now. If we look at the shape of the population value, the shape of this is very right skewed. It's a very right skewed distribution. However, when we look at samples that are of size 40, we know that because this value is bigger than 30, because n is greater than or equal to 30, by the central limit theorem, by CLT, x bar is going to be approximately normal, right? And so notice the answers are skewed left, well, no. Skewed right is the original distribution, the population, no. Approximately normal here should be the answer. Approximately normal should be the answer right here, all right? So the next one talks about the central limit theorem again, but it actually talks about when you describe the distribution, give me the mean and the standard deviation. It says an automobile insurer has found that repair claims have a mean of $920 and a standard deviation of $870. Suppose that the next 100 claims can be regarded as a random sample from the long-run claim process. So we know that our n is equal to 100. And again, anytime we have a sample size, we want to check to see if it's bigger than 30. So n is greater than or equal to 30. And by central limit theorem, x bar follows an approximately normal distribution with the mean of the population, that here is 920, and a standard deviation equal to what we call our standard error, which is going to be the standard deviation of the population, which is 870, divided by the square root of the sample size, which is 100. And square root of 100 is just 10, so it's 870 divided by 10. That's just $8.07. 70 cents. So our answer here is going to be B. Now, next question plays off of that and says, using that same scenario, the probability that the mean of the next 100 claims is larger than $1,000, approximately. So again, what we're going to do, we're going to draw a normal curve because we know it's approximately normal from the central limit theorem. The mean of the distribution is at 920. $10,000, so the probability that your x bar, your sample mean, is greater than 1,000, I'm sorry, not 10,000, $1,000. 1,000 sits over here. We want to be larger than that, so we're going to shade to the right. This is just a normal CDF problem. Normal CDF. And we know that our lower bound here is this starting value, the starting shade at 10,000, in 1,000. Upper bound is 999. You need at least 4, or at least 5 this time. The mean is 920. And the standard deviation here, or the standard error, will be calculated earlier, which is 8.7. So when we calculate this value, we're going to get a value that is very close to 0 here. As a matter of fact, you actually might get 0 in your calculator. And so the answer here is going to be E. So I actually skipped over problem 7 and 8 because now I just want to talk about these free responses that we're going to do, all right? And so 7 and 8 just talk about the central limit theorem. And we're going to work on these actual free response problems. So this first one talks about, I want you to show all the work. So let's go through this problem. It says, the weight of Granny Smith apples from a large orchard are normally distributed. At any time we see this word normally distributed like this means we're going to draw some kind of normal curve. They tell me that the mean is 380 grams and the standard deviation of 28 grams. So I know that X is approximately normal with the mean of, remember I write my parameters, 380 and 28. And so the first one says, a single apple is selected at random from the orchard. What's the probability that it weighs more than 400 grams? So I want to find the probability that X, one apple, is greater than 400 grams. Well, remember, we draw a normal curve. And on this normal curve, we have a mean of 380. And we're going to place 400 on the right side. Let's say greater than that value, right? And so we're going to do normal CDF. We know the lower bound here is 400. Upper bound is a bunch of 9s, at least 4. Mean is 380. Standard deviation is 28. So we plug that into our calculator. And I get a value that's equal to 0.238. So the next problem says 3 apples are selected at random from this orchard. What is the probability that their mean weight? So I've selected 3 apples. So now my n is equal to 3. And even though n is not bigger than our standard 30 that we need, we know the distribution is already normal. And because the distribution is already normal, by CLT, we're looking at the mean of the weight for those 3 apples, so that's X bar. Now follows a normal distribution, with the mean equal to the population, which is 380. And a new standard deviation called the standard error, which is 28, the old standard deviation, the population standard deviation, divided by the square root of the sample size. Anytime we have a sample size, anytime they give us any kind of sample size, we have to divide by the square root of it. And so this is going to clean up to be 16.166. So this is going to be 16.166, the new standard deviation, or what we call our standard error. Notice that it is smaller than the original standard deviation, the population one. It should always be smaller. That's because the more you look at, the less the variation there is in the sample. And so if we draw a normal curve, we're looking at the exact same thing. This time though, on the normal curve, the only thing that's going to change, we're going to do normal CDF. We're still at 400. We're still going to be bigger than 400, and it's still 999. The mean is still 380, and our standard deviation here is going to be 16.166. So we calculate this value. So writing out this statement, we're going to write out the probability that X bar, because it's a mean of a sample, is greater than 400. That's equal to 0.108. And notice that the probability decreased when you had an actual sample. There's going to be a smaller chance of getting that value because your values should be closer to the actual mean value of the population. So it says explain why the probabilities in A and B are not equal. And that's because in A, you looked at a single value. You looked at a single apple. B, you looked at a group of apples. The group should always have less variation than a single apple. So as the sample size increases, as the sample size increases, variation tends to decrease. And that's because when you increase the sample size, you're starting to make the sample itself look more and more like the population. So as we increase the sample size, we're going to decrease our variation. By decreasing the variation, you actually decrease the probability of rare events occurring here. All right, so looking at this example, it says an opinion poll asks a sample of 500 adults whether they favor giving parents of the school-age children vouchers that can be exchanged for education in a public or private school. Suppose that in fact 45% of the population favors this idea. It says, what is the mean of the sampling distribution of p hat? The proportion of adults in samples of 500 who favor giving parents of school-age children these vouchers. So we say p hat. Remember, we need to define what p is. Well, p itself is the true proportion. The true proportion of parents who favor the vouchers. Right? And that means we know that p itself, p is equal to 0.45. And from p we can find q, which would be equal to 0.55. And we know that n in this particular case is 500. So because of that, p hat follows a normal distribution. The mean of the population, which in this case is 0.45, and the standard deviation, which is the square root of p, 0.45, times q, 0.55, divided by the sample size, which is 500. That's equal to, if you simplify that, 0.0222. So this is the distribution of p hat. So what is the standard deviation of p hat? Well, the standard deviation of p hat, we just calculated that. The standard error, or what we call sigma p hat, is equal to, again, the square root of 0.45 times 0.55 divided by 500. We just got that to be 0.022. So check that you can use a normal approximation for the distribution of p hat. So two things we really need to check. The first one is that what we call our 10% rule. Surely 500 adults of school-age children. Surely 500 adults is less than 10%. 500 adults are less than 10% of all adults in the population. And the other thing we need to check is that the Normality Clause, which says that n times p greater than equal to 10, n times q greater than equal to 10. In this case, n times p, so that's 500 times 0.45. That is 225 people. So that means that that's 225 is greater than equal to 10. And then 500 times 0.55 has to be greater than equal to 10. So that's 275 people. So because this condition is met, we know that it follows an approximate normal distribution. So what's the probability that more than half of the sample are in favor? So if more than half the sample are in favor, we've checked conditions. We stated what p is. We stated the parameter for p. The last thing to find is probability. We know that it now follows a normal distribution where the mean is sitting at the mean of the population, which in this case was 0.45. More than half, 0.5, as it sits to the right of that. So we want to find the probability that p hat itself is greater than or equal to 0.5. They told me that the p hat for the sample, p hat is the sample, and that's the sample is half. So that's where I get that 0.5 from. So I'm going to do normal CDF, where the lower bound here is the 0.5, the upper bound is a bunch of 9s, The mean here is 0.45, and the standard deviation, or the standard error, is what I calculated to be, is 0.022. I get 0.012 when I calculate this. The last one is another proportion problem, and it says that George is a big fan of music from the 60s, and 22% of the songs on the MP3 player are Beatles songs. Suppose George sets his MP3 player to shuffle so that it selects songs randomly. During a long drive, George plays 50 randomly selected songs. What is the mean and standard deviation of the proportion of the 50 randomly selected songs that are Beatles songs? So again, we want to define our variable, define what the parameter is. So P is the true proportion of songs that are Beatles songs. And we know that P here is equal to 0.22, which means that my Q is equal to 0.78. If I want to find the standard deviation of P, or sigma P, hat is the square root of 0.22 times 0.78 divided by my sample size, in which case is 50. And I get a standard error equal to 0.059. Calculate the probability that more than 30% of these things, and we know that because, checking our conditions real quick, n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. So let's check that real quick. We have 50 times 0.22. That's equal to 11. Has to be greater than or equal to 10. So that's 11 is greater than or equal to 10. That checks out. And then the other one would be 50 times 0.78 has to be greater than or equal to 10. And that's going to be 39. It's greater than or equal to 10. So both those check out. Because of that, we know the distribution is going to be normal. And because it's going to be normal, I want to find the probability that it is X, or that P hat in this case, more than 30. The P hat here is 0.3. So I want to be greater than 30, or 0.30%. Draw your normal curve here. The mean is at 0.22. Greater than 30 is here at 0.3. Shaded to the right. This is normal CDF. Lower bound here is at 0.3. Upper bound is a bunch of 9s. The mean, 0.22. And the standard error is what I calculate up here. That's at 0.059. So when I calculate this, I'm going to get this is equal to 0.088.